You know, it's one thing to have a chatbot draft a polite email to your boss for you.
Right, like a simple text task.
Exactly. Like if it hallucinates or makes a mistake,
Yeah.
maybe you sound a little robotic or, you use a word you would never actually say out loud.
It's an embarrassment, sure, but it's not a disaster.
Right. But it is an entirely different reality to hand in AI the actual keys to your personal banking, your web browser, and your local file system.
Oh, absolutely.
And then to just tell it to, well, handle things.
Because the stakes escalate from a minor social embarrassment to a catastrophic system compromise in literally the blink of an eye. And because we are pushing for greater autonomy, we are actively handing over those keys way faster than we are building the locks.
Which is exactly why we are unpacking this today. We're going on a deep dive into the cutting edge of where artificial intelligence meets cybersecurity.
It's a fascinating space right now.
It really is. Our source material today is a recent state-of-the-art survey featured on the Gen AI Foundations, put together by researchers from UC Berkeley, UIUC, and UC Santa Barbara.
Yeah, brilliant team.
They mapped out the attack and defense landscape of agentic AI. And for you listening, if you are building, using, or even just, thinking about autonomous agents, this framework is essential. We are moving way beyond the theoretical here into active exploitation.
We really are. And, to understand the threat landscape, we have to look closely at the architectural paradigm shift.
The core premise, right?
Exactly. The core premise we're dealing with is the transition from isolated large language models, where you just input text and receive text in a closed loop, toward these hybrid systems. Right. We're taking that reasoning engine and wiring it directly into diverse software components. We're giving the model persistent memory, access to runtime environments, and an entire arsenal of tools to interact with the outside world.
Okay, let's unpack this, because I think the best way to really visualize this shift is an analogy.
I love a good analogy.
Right, so a traditional LLM, like the chatbots we've all been using for the past couple of years, is essentially a highly advanced magic 8-ball.
Mm-hmm.
You ask it a question, it shakes up its internal parameters, and it gives you a static answer.
Mm-hmm.
But agentic AI is like a robotic butler.
A very capable butler, yeah.
Right, it doesn't just answer a question. It plans a sequence of steps. It reaches out and grabs physical tools, and it actively modifies your environment to get the job done.
That's spot on.
But here is my pushback to you on this. Isn't the whole point of these agents to be as flexible as possible? Like, we want the robotic butler to be able to do whatever we ask, whenever we ask it. Why is that flexibility suddenly a massive vulnerability?
Well, it creates a vulnerability because in system design, flexibility and security are almost always engaged in this zero-sum tug-of-war.
Right, you can't have both.
Exactly. The researchers lay out 7 distinct design dimensions to illustrate this. And whenever an architecture moves the slider from, say, least flexible to most flexible on any of these dimensions, the attack surface expands exponentially.
Wow. Okay, what's an example?
Consider input trust. A closed system relies on zero external data, right? Your trust boundary is solid.
Because it's completely isolated.
Right. But for your robotic butler to actually be useful, it needs to process arbitrary external data from the open web. The moment you allow arbitrary web parsing, your trust boundary just shatters completely.
Because it's suddenly ingesting and analyzing text or code or images
Yeah.
that literally anyone with an internet connection could have published.
Exactly.
It's pulling in the complete chaos of the open internet and treating it as valid input.
Exactly that. Now compound that with the workflow dimension. Traditional software relies on deterministic, developer-defined workflows.
Like predictable steps.
Right. You click a submit button and it triggers a specific, unchangeable database script. But modern agents shift to dynamic, LLM-defined action sequences.
They decide what to do next.
Yes. The AI uses probabilistic reasoning to decide what its very next step should be based on its current context. So, if an attacker can manipulate that context, they aren't just breaking a script, they are hijacking the entire cognitive control flow of the system.
It's essentially writing its own operating rules on the fly.
Exactly.
So if you feed it malicious context...
It writes malicious rules.
Man, that is wild.
That is the core of it. We also have to evaluate access sensitivity and action. An agent might start out performing benign read-only tasks like summarizing a public Wikipedia article.
Sure, harmless stuff.
But true flexibility means granting it access to PII, banking details, or proprietary enterprise data, and coupling that with environment-modifying operations. We are talking about granting execution tools.
So to stick with the analogy, It's the difference between asking the butler to read a recipe out loud
Mm-hmm.
versus letting the butler turn on the gas stove and start chopping vegetables with a really sharp knife. The blast radius of a mistake is entirely different.
The blast radius is everything. And the remaining dimensions they outline, memory, tool use, and user interface, they just accelerate that risk.
How so?
Well, we're moving from a blank slate every session to persistent memory that spans months. We're shifting from a predefined set of internal tools to agents that can dynamically select and download arbitrary third-party tools on their own.
Oh, wow.
Yeah. And we're moving from simple text boxes to multimodal interfaces where the agent interacts directly with raw code environments.
Right.
Every single step toward that fully autonomous capability creates just a tangled web of new vulnerabilities.
So if that is the sprawling architecture, how are adversaries actually getting in? Because, I mean, if the system is doing all this dynamic reasoning, an attacker doesn't necessarily have to brute force a password anymore, do they?
That's right. The threat models categorize adversaries based on their access level. So you have external, user level, and internal.
Okay.
And the most startling reality of agentic systems is that an external adversary can launch a devastating compromise without ever directly communicating with the agent.
Here's where it gets really interesting. When we look at indirect prompt injection, I mean, it is a complete mind bender for anyone used to traditional cybersecurity.
It really is.
Going back to our analogy, it is like sending your robotic butler down to the local library to research a topic for you. But an attacker knows your butler is going there.
Right.
So the attacker goes to the library beforehand and hides a booby-trapped sticky note inside the specific book the butler is going to read.
A perfect analogy.
And that note contains a new set of malicious instructions disguised as text. So the butler reads the book, processes the note, and suddenly it's following the attacker's orders, completely overriding your original request.
What's really fascinating here is the underlying mechanism of why that actually works.
Yeah, how does it get fooled so easily?
Well, in traditional software, data and instructions are kept strictly segregated. But large language models process everything. Your system prompt, the user's request, and the text scraped from a web page as just one continuous stream of tokens.
It's all just text to the model.
Exactly. The model relies entirely on semantic understanding to differentiate between this is a rule I should follow and this is data I should analyze.
Right.
So an attacker exploits that probabilistic blending by crafting text that the model misinterprets as a high-priority instruction.
And the threat gets even deeper and frankly weirder when we look at internal adversaries manipulating the agent's actual brain.
Yes, absolutely.
The research dives into model poisoning and memory poisoning. And I gotta say, memory poisoning sounds like a plot device from some dystopian sci-fi movie.
It really does, but the mechanics are totally grounded in how modern AI memory functions. You see, agents don't store memories like text files in a folder.
Right.
They use vector databases. So they take a piece of information, run it through an embedding model, and turn it into a high-dimensional mathematical vector. It's essentially a coordinate in a massive numerical space.
Okay, so it's retrieving past information based on mathematical similarity rather than exact keyword matches.
Correct. So attackers use a technique called semantic injection. They leverage contrastive learning to craft factually incorrect, highly malicious content that mathematically matches the embedding space of legitimate queries.
Wait, I'm trying to wrap my head around this. So they are basically taking a lie and optimizing the math behind the words so that the database categorizes it right next to the truth.
You're hitting on the exact mechanism. Even if the malicious text uses entirely different vocabulary than the user's query, the attacker has manipulated the vector weights.
Unbelievable.
Yeah, so when the agent searches its memory for a specific safe topic, the similarity search preferentially retrieves the poisoned knowledge instead of the correct data. The agent is literally retrieving fabricated memories and using them as a foundational truth to plan its next action.
And we are already seeing the real-world fallout from this. The sources make it super clear we aren't just talking about theoretical lab experiments or academic white papers here.
Not at all.
Attackers have used prompt injection to seamlessly extract source code from private GitHub repositories.
Yeah.
There are documented remote code execution vulnerabilities where attackers gain full, unauthorized shell access to the underlying system.
Right.
And they are already exploiting web agents to gain unauthorized access to personal banking interfaces.
The severity is undeniable. And the researchers highlight a critical dynamic here, which is that these attacks are so effective because of system-level risk interactions.
Okay, what does that mean?
Well, the architecture is so interconnected that vulnerabilities don't just exist in a vacuum, they cascade. It's a domino effect where a minor compromise at the edge of the system triggers a catastrophic failure at the core.
I want to break down one of these cascades because the mechanics are fascinating. Let's look at the echo leak attack that they detailed in the research. Walk us through how a cascading failure actually plays out.
Sure. Consider an enterprise environment where an AI agent is deployed to manage emails. In an echo leak scenario, an adversary simply embeds a malicious document, say, a seemingly benign PDF, and emails it to an employee.
Okay, simple enough.
Right. That is the initial compromise exposing the agent's untrusted interface to malicious input. Then later, the enterprise's AI agent runs a routine retrieval pipeline to summarize the day's inbox.
So it opens the PDF to read it.
Yes. And because of the probabilistic blending we discussed earlier, the agent's logic flow is completely hijacked by the instructions hidden in that PDF.
Wow.
This triggers a secondary failure, which is unconstrained data flow. The agent abandons its summarization task. Instead, it begins silently gathering highly sensitive user data from other emails in the inbox.
Just reading everything.
Everything. It then formats that data and executes an API call or a Python script to exfiltrate the payload directly to an attacker-controlled server.
And the most terrifying detail about echo leak is that it happens entirely in the background. Zero user interaction is required.
None.
Like, the employee didn't click a phishing link.
Yeah.
They didn't download a shady executable file. They simply received an email, and the robotic butler, trying to be helpful, processed the inbox, got brainwashed by a sticky note, and literally mailed the house keys to a thief.
That profound autonomy is the ultimate double-edged sword. You've removed the human from the loop, which means you've also removed the human's common sense and skepticism.
Absolutely.
And this domino effect doesn't just apply to data exfiltration. Attackers are also figuring out how to weaponize the model's own inherent cognitive flaws.
Oh, this brings up what I thought was the most brilliant and totally diabolical exploit in the entire survey: hallucinated packages.
Yes.
The echo leak scenario relies on the attacker feeding the agent bad data. But what happens when the attacker doesn't even need to supply the bad data? We all know LLMs hallucinate.
They do.
They confidently invent facts, or in the case of coding agents, they invent software libraries that don't actually exist to solve a programming problem.
Right. It's a known vulnerability. An LLM might be asked to parse a specific type of database, and it hallucinates an import command for a package called, I don't know, db parser utils v2.
Because it sounds right.
Exactly, assuming it exists because it conceptually sounds like something that should exist in its training data.
Right. So attackers are monitoring coding agents, figuring out the names of these fake, hallucinated software packages that the models frequently imagine.
Right.
Then the attackers go to real software registries like NPM or PyPI, and they actually register those fake names and upload malicious code under those titles.
It is a stunningly elegant supply chain attack. They are turning a known cognitive weakness of the neural network into a highly reliable delivery mechanism.
It's crazy.
When the agent is dynamically writing a script to solve a user's problem, it decides to download that package it just imagined. But now, because the attacker made it real, the agent reaches out to the registry, downloads the attacker's malware, and executes it directly in the host environment. The agent literally infects itself.
It's turning the AI's imagination into a weapon against the user. So given the sheer creativity of these attacks, we clearly cannot just let these agents run wild in production. How on earth do we play defense on the fly against a system that basically writes its own rules?
Well, the primary line of defense focuses on runtime protection. Because agents are highly dynamic, your security architecture must operate dynamically.
Makes sense.
This primarily takes the form of input and output guardrails. Input guardrails validate, sanitize, and classify the data before it ever enters the agent's reasoning process. Output guardrails verify the agent's intended actions, checking the code or the API call before it executes in the real world.
So it's like rigorously inspecting the groceries before they are allowed in the house and then meticulously checking the meals before they are served to the dining room.
That's it. But this raises an important question, though. How strict do you actually make those checkpoints? The research outlines a fundamental, almost painful trade-off here.
Okay, what's the trade-off?
If you use strict rule-based detection, like an immutable list of allowed URLs or hard-coded regex patterns to block specific words, it is highly secure. But it is incredibly brittle. It destroys the very utility of having a flexible agent.
Right, if my robotic butler can only shop at 3 pre-approved stores and can only cook exactly 4 meals, I don't really have an autonomous agent. I just have a very complicated script.
Exactly. So to maintain utility, developers often switch to model-based detection. You use a secondary specialized AI model to monitor the main AI's inputs and outputs.
Oh, an AI watching an AI.
Right. But that introduces massive latency and heavy computational overhead. Plus, the boundaries between safe and unsafe in natural language are deeply ambiguous.
Yeah, language is messy.
Very. A prompt might look like a benign request to summarize an article, but structurally contain an exploit. This leads to a high rate of false positives, where the guardrail blocks legitimate helpful tasks and false negatives, where clever semantic injections slip right through the secondary model's radar.
Okay, so if scanning everything at the door is unreliable because the language is too ambiguous, what about tracking the data once it's already inside the house?
Tracking the data flow.
Yeah, the researchers discuss information flow control, or IFC, and taint tracking. To me, this is like putting an invisible UV dye into a river of data. You tag the untrusted information the moment it enters from the web, and you track that glowing water as it flows through the agent's internal cognitive systems.
That's a great visual.
The goal is to make sure that glowing, untrusted data never spills into high-privilege areas, like an email app box or a shell terminal.
That is a perfect conceptualization of taint tracking. You ensure that any variable labeled untrusted mathematically cannot influence an operation labeled execution.
But there's a catch, I assume.
A big one. Enforcing this inside a probabilistic large language model is a monumental engineering challenge. Unlike traditional software where data moves in discrete, trackable variables, an LLM processes text through dense matrices of neural weights.
Oh, right. It's a black box.
Exactly. Tracking that UV dye through billions of parameters requires running multiple parallel executions or using complex symbolic variables. The runtime overhead is just staggering. For an agent that needs to react in milliseconds, it's often practically impossible to implement without bringing the system to an absolute crawl.
Which naturally brings us back to the most basic low-tech solution available. Just ask the human.
Good old human in the loop.
Right. We see this implemented all the time with tools like GitHub Copilot. It's called human in the loop, or HITL.
Yeah.
The agent wants to run a terminal command, so it pauses its workflow and pops up a dialog box saying, "Can I execute this?"
Yes.
But I have a massive issue with this approach. Doesn't that just lead straight to alert fatigue? If my agent asks me for permission every 5 seconds, I'm not going to read the terminal command. I'm just going to start blindly clicking allow always, exactly like I do with those endless browser cookie banners.
You are identifying a major vulnerability in human-in-the-loop systems, the psychological burden placed on the user.
It's exhausting.
It is. If the alerts are too frequent, or if they require a deep level of technical literacy to actually understand the risk of the command, the security mechanism completely fails. Users will either blindly approve risky actions just to get their work done, or they will get so annoyed they dive into the settings and disable the guardrails entirely.
I would definitely be tempted to turn them off.
Right. So the research emphasizes that we desperately need principled criteria for when to defer to human judgment. We have to use machine learning to predict user preferences and dynamically assess the risk of an action, only interrupting the human for truly anomalous or high-stakes decisions to prevent that exhaustion.
So runtime defenses like the guardrails, the UV dye tracking, the human alerts, they are necessary layers, but they're all inherently flawed. They'll have massive trade-offs in latency, utility, or user experience. It sounds like we are basically trying to slap a Band-Aid on a gaping architectural wound. We can't just patch these systems after the fact.
We absolutely cannot, and that is the crux of their final defense strategy. We must build these systems secure by design. Security cannot be an afterthought bolted onto the outside. It has to be baked into the very topology of the architecture.
Okay, so how do we do this?
The primary method they advocate for is privilege separation.
Oh, like the military.
Yeah.
Need-to-know basis, compartmentalized intelligence.
That's exactly the mindset.
Ah.
Instead of deploying one massive monolithic LLM that handles everything from reading emails to executing code, you split the architecture into specialized roles. You deploy planners.
What do planners do?
They are high-privilege agents that determine the workflow, hold the system prompt, and manage the task goals. And you strictly isolate them from processors. Processors are low-privilege components sandboxed away from the core logic. Their only job is to handle the raw, untrusted data.
Oh, I see. So if a processor agent is assigned to read that booby-trapped library book with the malicious sticky note we talked about earlier, the semantic injection might still trick it.
It might.
But it doesn't matter, because the processor physically lacks the API keys or the network permissions to execute a tool. All it can do is pass a sanitized summary back to the planner.
Exactly. You enforce an architectural gap that physically prevents untrusted data from dictating tool calls. The survey also introduces a critical security paradigm tailored specifically for agents called contextual security. This is actually adapted from the concept of contextual integrity in the data privacy world.
Okay, how does contextual security differ from the standard InfoSec stuff we've been doing for decades?
Well, traditional security focuses on the CIA triad, which is confidentiality, integrity, and availability. Contextual security adds a behavioral layer. It governs the prioritization of the agent's context window.
How does that work in practice?
It ensures that an agent's actions remain strictly aligned with the user's intended original task, regardless of what data it ingests later. It is designed to prevent context drift or instruction overrides.
Oh, that's smart.
Yeah, so if the user's intent was to summarize an article, contextual security protocols mathematically weight the system prompt heavier than the retrieved snippets, ensuring the agent doesn't get hijacked by malicious environmental data telling it to drop the summary and run a script.
So keeping the robotic butler strictly focused on the grocery list and engineering it so it physically cannot get distracted by a billboard outside.
Exactly.
But wait, if we are dividing this up into planners and processors, and we are moving toward massive multi-agent systems where different agents constantly communicate with each other, how do we keep track of who an agent is even working for at any given millisecond?
That is where identity and access management, or IAM, really has to evolve. Traditional software uses static user identities. You log in, you get a session token, you stay logged in.
Right.
But agents act on behalf of users, and they do it dynamically across lots of different applications. The researchers contrast our current centralized identity providers, like the single sign-on we use at work, with decentralized protocols.
Yeah.
They point towards standards like the W3C decentralized identifier, or DID.
So what does this all mean for the actual nuts and bolts of the architecture?
It means we have to move toward a world of transient task identities. An agent doesn't just log in with your credentials permanently. It is issued a short-lived identity specifically scoped to one single task.
Oh, we're locked down.
Yes. It uses a secure token vault to manage its API keys, checking them out and returning them. This level of granular, time-bound access control is how we keep an agent from going rogue, especially when your agent has to interact with a third-party agent.
Right, because you don't trust the other agent either.
Exactly. You need cryptographic proof that you are only granting access to exactly what is needed for that specific interaction, preventing a compromised subagent from illegitimately leveraging your agent's capabilities.
It is like giving the butler a corporate credit card that only has exactly enough money for the groceries on the list, and the card mathematically self-destructs after 1 hour. It heavily limits the blast radius of any potential compromise.
That limitation is the entire goal of Secure by Design.
Man, this is a tremendous amount of architecture to rethink. As we wrap up today's deep dive, I think the biggest takeaway for you, the listener, is a fundamental mindset shift.
Definitely.
As you start integrating more AI agents into your personal workflows or your enterprise pipelines, you need to realize you aren't just installing software updates anymore. You're essentially hiring autonomous workers. And just like with human employees, you have to think critically about what data they can access, what tools they can wield, and what structural guardrails are keeping them aligned with your actual goals.
If we connect this to the bigger picture, we really have to ask ourselves a daunting question about the future of the internet. If we are rapidly moving toward an ecosystem of massive multi-agent systems where agents have their own decentralized identities and they actively delegate subtasks to completely different agents built by different companies, how do we handle accountability and liability?
That's a huge question.
When a chain of 5 different autonomous agents makes a catastrophic error, all triggered by a single poisoned memory vector from 3 sessions ago, who is ultimately responsible for the blast radius?
That is a terrifying but entirely necessary puzzle that developers and security teams have to solve immediately. We started out hoping for a magic 8-ball, but we built a robotic butler. Now we just have to make sure we don't accidentally hand it the keys to the entire neighborhood. Thanks for joining us on this deep dive into the architecture of autonomous AI. Stay curious, stay secure, and we will catch you next time.